We have derived many equations to calculate the stress and strains in the pressure vessels, in cylindrical shaped or spherical shaped pressure vessels. And you can use them to directly calculate the stress and strain and then compare them with the strengths or allowable deformations to make sure to examine if your design thing or existing structure is safe enough. Otherwise, you can also do some inverse problems. If you have been given the allowable stress, you have been given the materials and the overall size of the vessel, you can design the thickness of the vessel to make sure it's safe. And if you're not given a material, you may be also requested to design it by selecting a material, by selecting the modulus of elasticity, etc. Okay. So here in this example, we will deal with a design problem. This is just use the equations in the inverse manner. Okay. A steel spherical tanker with a diameter of 12 meters is shown here, and the inner pressure is 22 kPa. Then design the required wall thickness if a factor of safety is 6.7. Then the tensile strength, the yield stress or the tensile strength has been given for the steel material, that is 350 MPa. Then design it by selecting a thickness, and then if you're given with this thickness, how much would be the change in the diameter of the tanker in that case. Okay, so here you just need to use these two equations. Since this is a spherical shape, it will be relatively easy. So you have one equation that you can use for stress analysis in the first step, and for strain analysis for the second step. Okay, let's look at the first step. In the first step, our task is to design the thickness. Design the thickness against normal stress, right? Not shear. The shear is not given at all, right? So we have to examine the normal stress, it's sigma A, right? So our sigma A, the equation we have known, right? The sigma A equals PD over 4T. You have to make sure that it's not higher than allowable normal stress. So this is the yield stress. Is that all? We have been given a yield stress, but also a factor of safety. Let's review the concept of the design problems in earlier chapter, right? How to design, how to do the design. We will never actually, in practical design, we will never use the materials to its strengths. We have to make sure that the service load generated stress is much lower than the yield stress. Okay. Normally, we introduce a concept of factor of safety. You just use the yield stress over factor of safety as the allowable stress. Okay. So this is just the equation or the algorithm we'll use to finish this design task. Okay, then let's list the parameters that have been given. So the pressure, we have known that is 22 kPa or 0.022 MPa. Diameter D is 12 meter or 12,000 millimeter. Okay, we're unifying the unit into MPa, Newton meter things. Okay, then the T is unknown. That is what we need to design. Right, the yield stress 350 MPa, and factor of safety 6.7. Okay. Then here we can use these numbers to do our calculation. That would be sigma A would be 0.022 MPa times 12,000 millimeter over 4T. This should be not larger than 350 over factor of safety 6.7. Okay, you can solve it very easily and get that T should be not smaller than 1.263 millimeter. Okay, to make sure your tanker is safe, the thickness of the wall should be larger than 1.263 millimeter. Then let's examine, let's calculate the change in diameter in this case. Okay, this is our second step. Change in diameter if the thickness is just at 1.263 millimeter. Okay, so here the delta D can be calculated from D times epsilon A. Right, so here we just need to calculate the epsilon A. Right, the epsilon A equals PD over 4TE times 1 minus Poisson ratio. Okay, so this is 0.022 times 12,000 over 4 times 1.263 millimeter times the E is 200 GPa and Poisson ratio is 0.3. Okay, so here we have 200,000 MPa, right, times 1 minus 0.3. Okay, so here it would be 183 microstrain. Then the diameter change will be calculated as D times epsilon A. The D is 1/2000 times 183 micro. Right? So here you get 2.19 millimeter. This is the increasing of the diameter of the vessel when it's subjected to the pressure. That's it. So you can see that we just designed the thickness of a tanker, of a spherical shaped pressure vessel. Okay, so this is relatively simple, but if you are dealing with a capsule or cylindrical pressure vessel, it will be more complicated. But I believe you can also do it. Just keep in mind that you just need to calculate the stress. Just for any type of design, you just need to leverage the all given parameters to calculate to derive the expression of the stress, and then compare it with the allowable stress value. Then you can derive the parameter required for design. It can be the site, or it can be other parameters. Okay.